you look at the natural world, you see all kinds of complex phenomena. What is the foundational origin of that kind of complexity that we see in nature? And so at first I thought, oh, I know all this quantum field theory and mathematical physics and so on, things like, how does a snowflake grow? I'm going to be able to just crush that problem with all of the mathematical methods I know. Well, it didn't work out that way.
Hello, Stephen.
Hello.
I think we're going to make a start soon.
Great. Yes.
Welcome, everyone, to our special Physics and Astronomy Colloquium. And we have none other than Stephen Wolfram himself. He's going to be telling us about what he's been thinking about lately. I'll leave him to tell us that. I'm not going to say too much, but I'd just like to take this opportunity to thank the Institute of Physics for supporting this colloquium and the School of Physics and Astronomy for making this happen. So, without further ado, I think I'll just hand over to you, Stephen.
Thanks. Well, let's see. So these are very busy and exciting times for me because a lot of things I've been building in science and separately in technology seem to be coming to fruition at the same time, which is really cool, but really intense. So a lot of things that we've been doing on the Mathematica, Wolfram Language, Wolfram Alpha side have kind of been merging with a lot of things that have been happening in the world with AI. We used to have lots of human users only. Now we also have lots of AI users, and that's been pretty interesting, and a lot of exciting things happening there. And a lot of things to do with science about AI are also a lot of things I've worked on in science also are turning out to be relevant to the foundations of AI. But the other thing that's been happening the last 5 years has been tremendous progress in understanding things about fundamental physics that I'm really excited about. Actually, it's extended beyond physics because it's turned out that the formalism that we built for thinking about foundations of physics also turns out to be relevant to the foundations of a whole bunch of other fields: mathematics, biology, machine learning, and so on. So, okay, well, let me try and tell you a little bit about what we figured out and how things look going into the future. I should first sort of go backwards a bit, because a lot of what I've done recently has sort of built on things that I worked on about 45 years ago. At that time, when I was a kid, a teenager, I was doing particle physics and cosmology and so on in the late 1970s and so on, at a time when that was really an exciting field. And I was excited to be able to make some contributions there, which seem to have even survived the test of time. But I then got interested in sort of a foundational science problem, which is you look at the natural world, you see all kinds of complex phenomena. What is the foundational origin of that kind of complexity that we see in nature? And so at first I thought, oh, I know all this quantum field theory and mathematical physics and so on, things like, how does a snowflake grow? I'm going to be able to just crush that problem with all of the mathematical methods I know. Well, it didn't work out that way. So I started thinking, well, what if we're going to take the idea of theoretical science, how can we sort of roll back a bit, zoom out a bit, ask what are the sort of foundations of thinking about theoretical science that we can then sort of take another run at these kinds of seemingly everyday types of problems? And what I realized is that if you're making models of things, it's important that you have some model of things, but what should that model be made of? What had been traditional for 300 years or so in exact science is to use mathematics and mathematical equations and calculus and all those kinds of things to build models of things in the world. But so what I sort of was thinking about was, well, what are the sort of primitives from which you can build models? And what one wanted to do there is to sort of think about, well, models are some rules for how the world works. How can one represent those rules? And sort of the thing at that time, I had been very involved in the practicalities of building computer languages and so on. And so sort of the obvious thing to me was, okay, let's use programs as sort of the raw material for building models of things. And so that's what I got started doing at the beginning of the 1980s. And let me tell you a little bit about what I found. Some of this is very well known at this point. But let me just sort of bring you up to speed on that. And some of the phenomena that I discovered there will end up being sort of the core phenomena which let us understand things, I think, about fundamental physics now. So let me see. Let's try and share my screen. Oops. Okay. There. Okay. So the question is, if we're going to make kind of models of the world using programs, what kinds of programs might they be? And something that I started off doing long, long ago is to use these things called cellular automata to study that. And here's a typical example of a cellular automaton. The way the system is set up, it's just got a line of cells. Each cell is either black or white. And then in a series of steps, you update the color of each cell according to this rule that says, based on the colors of the cells on the row above, what should the color of the cell on the next row be? So, okay, so we're going to use that rule, and let's just make a picture of what happens with that rule. And of course, I'm using Wolfram language, which is kind of my I feel like I've been living kind of the AI dream now for 40 years, because it's kind of the AI dream is sort of you imagine something you want to do, and then as automatically as possible, you get it done. And that's kind of, I've been building this whole collection of tools to basically get to the point where I can kind of have an idea about something and as efficiently as possible kind of work out that idea. And that's kind of been the thing that's allowed me to do basically all the science that I've done. By the way, I just might mention for in modern times something if, for people who are actually are into using tech, the new notebook assistant that we have, where you can just kind of ask something in natural language. I might do that in a minute, but let's do this. I know what I'm doing here, so I don't need to ask for help right now. But anyway, so we've got this rule, and we've started it off from one black cell here. It's a very simple rule, and it makes this very simple pattern. Okay, let's try a different rule. Let's say we change what the outcomes from these different cases are. Let's run with that rule here. Let's do that. Okay, so now again, we've got simple rule, simple behavior. We might have thought at this point that there must be some kind of sort of meta theorem that says if our rule is simple enough, the behavior we get must somehow be correspondingly simple. Okay, let's try changing the rule a little bit more. And let's do that. Okay, so now we get a slightly more elaborate pattern. Maybe I'll run it for a bit longer. And oops, I keep on run it for a bit longer. Oh, that was the wrong thing. Run it for a bit longer, not to show the mesh here. And what we can see is that from this very simple rule, we get a pattern that is very intricate, but it's very structured. It's just a nested fractal pattern. So again, we might think, okay, our theorem might be, if we have a sufficiently simple rule, then even though the patterns we get might be quite intricate, they will still have some ultimate regularity. Okay, so then the obvious thing to do is a computer experiment. And it's gotten a lot easier to do this in the years since I first did this. But let's just say we look at all possible rules of this general type. There are 256 of them. Let's just look at all of them, and let's just see what behavior we get. And let's do that. So there's the result. So this is kind of like pointing our sort of computational telescope out into the computational universe and seeing what's out there. A lot of the time, what's out there is pretty boring. It's just things going off to one side or making stripes and so on. We keep going, we keep going, we keep going. Up, there's something interesting happening here. This is rule 30 and the kind of enumeration of these rules. And it's doing something a bit different. It's doing something a bit more complicated. We can keep going. We'll see other kinds of things happening. There are a few other cases where we see similar kinds of complicated behavior. Often we just see nested patterns and so on. But let's take a look at that rule 30 again. So let's look at its rule. It's very simple. It's just the same setup as before, but let's look at what it does. This is what it does. So to me, this is my all-time favorite science discovery. You just started off with one black cell up here, and you're just following this simple rule, and you get this very complicated behavior. And there's a certain amount of regularity that you can see over here on the left, but many aspects of this pattern are, for practical purposes, completely random. Like for many years, we used the center column of Rule 30 as the pseudorandom generator in Mathematica and Wolfram language and so on. It's been sort of the only surviving pseudorandom generator over the last 40 years that has been that's sort of still a surviving approach. So let's talk about what we see. This is kind of an intuition breaking thing, because we might have thought from our experience with things like engineering that if we want to make something complicated, we somehow have to go to a lot of effort to do that. We have to build up some complicated plan, complicated rules, and so on. But what this is showing us is that even with this incredibly simple rule, with this starting off from this very simple initial condition, we get this very complicated behavior. It's a surprising thing. It's something which I've come to think is kind of the key secret that nature uses to make the kind of complexity it makes. And we'll talk about that in a bunch of different domains later. But let's talk about kind of what this, sort of more of the big picture of what this means. So one question you can ask about this Rule 30 pattern is, what will it do after a billion steps, let's say? Now, what we might have thought, based on sort of our experience with mathematical science and so on, is that somehow it's a simple enough system, we must be able to find some kind of exact solution, some kind of formula for what will happen. That's what we've come to expect. When we feel like we're making progress in physics, we solve the two-body problem, for example, we can immediately say, where will the Earth be, at least in a first approximation, a million years from now, without having to trace those million orbits around the sun, so to speak. We can just fill a number into a formula and jump ahead. So the thing we might imagine from sort of our experience with mathematical science is, surely with a rule this simple, we must be able to do that in a case like this. And that's what I at first thought myself back when I first really started studying this around 1984 or so. But it turns out that's just not true. The kind of idea that you can sort of jump ahead, you can solve the system, is something that just won't work in a case like this. So there's sort of, if you want to know what happens after a billion steps in Rule 30, you can clearly just run it for a billion steps and see what happens. The issue is, can you jump ahead? Can you, in a sense, reduce the computational effort that you need to go through to find out what will happen? Well, it turns out there's a phenomenon that I call computational irreducibility, which I think is a very central and important phenomenon that we'll see showing up in all sorts of places in physics and biology, lots of different places. And I think it's sort of a foundational phenomenon. And what computational irreducibility is about is it says, actually, in a case like this, there isn't a way to jump ahead and say what the answer will be by some simple procedure. Instead, the only way, it's sort of what's happening here, this thing is doing an irreducible computation. The only way to find out what will happen is essentially to follow each step and see what happens, to do the simulation and see what it will do. Well, so how would one establish a result like computational irreducibility? Well, it's sort of related to a thing I call the principle of computational equivalence. And the principle of computational equivalence works like this. We say, how can we characterize, how can we get sort of a theoretical characterization of what's happening in a case like Rule 30? Well, we can think of what's happening in Rule 30 as being like a computation. It's starting from that initial condition, and then it's running a computation to see what will happen. So a question is, how does that computation compare with other computations that other systems do? And so we have this kind of comparison of computations. Each system is doing a computation. How do they compare? Well, the principle of computational equivalence says something that first is quite surprising. It says, if we start looking at all these different patterns and all these different things that happen, then beyond patterns that are obviously simple, everything that we see will be essentially equivalent in its computational sophistication. In other words, when we get above some sort of low threshold, we'll immediately jump to a place where all the things that we're looking at have the same level of computational sophistication. Now, we've kind of seen something like this before, 100 years ago, nearly 100 years ago, in sort of the idea of universal computers. Back at the beginning of the 20th century, one might have said, okay, we want to make an adding machine. Okay, we'll build this particular piece of hardware to make an adding machine. We want to make a square root machine. We'll build a completely different piece of hardware to make a square root machine. But then it turned out, with Turing machines and combinators and lambda calculus and all these different approaches, it turned out that it became clear that there was this universal idea of computation, that once you had a system of a particular kind, that you could, with that system, you could cover all these different computational possibilities, that you could make a universal computer that with appropriate programming, so to speak, could be made to emulate any other universal computer. And essentially, the principle of computational equivalence is a much tighter version of that kind of statement. It's a statement that it's not something where you can construct a universal Turing machine. Actually, a number of years ago, I now know what the very simplest possible universal Turing machine is, and it's quite simple. But you can construct this. You can make a computer. You can build that CPU chip to do computation. Actually, the principle of computational equivalence says that pretty much any system, as soon as it's not behaving in an obviously simple way, will behave in a way that sort of maxes out the computational capabilities it has. Okay, so what consequence does that have? Well, if we're looking at something like Rule 30, and we're saying, well, what's it going to do in the end? What we're doing in asking that question is to sort of set up a competition between us as the thing that's figuring out what's going to happen and the system itself just doing what it does. And we might imagine that, look, with our brains, our computers, our mathematics, whatever else, we're much smarter than this little system here with its tiny little rule here. So somehow we must be able to sort of jump ahead and figure out what will happen. But the principle of computational equivalence says that at some fundamental level, we can't be much smarter than this system. We will be equivalent in our computational sophistication to this system. And so that means that we're going and trying to figure out what the system is going to do. We're trying to jump ahead. Actually, we just won't be able to do that because this system is just as computationally sophisticated as we are. And that's what leads to computational irreducibility. We can't win that competition, so to speak. We are just equivalent to this system. And so the only way we can work out what the system is going to do is to follow the same kind of computation that the system itself does, just follow each step and see what happens. So that's kind of the idea of computational irreducibility. It's an important idea, both as we'll see in science, but also in kind of philosophy and in thinking about many kinds of things. Like, for example, a place where it shows up is in thinking about AI ethics. If you're trying to figure out, you've got an AI and it's doing all these things, and you ask the question, you say, I want to make sure my AI only does the right thing and never does the wrong thing. Well, in order to figure that out, you have to be able to sort of jump ahead and see everything that the AI can do. And what you realize is that if you're going to let the AI have sort of its computational sophistication, you have this choice. Either you can let the AI be computationally sophisticated, in which case it's going to have computational irreducibility, or you can say the AI is going to be constrained to be much simpler and we're going to be able to see, the cogs and wheels inside and see what it's going to do. But as soon as you say it's going to be sort of computationally sophisticated, you're going to have computational irreducibility, and you're not going to be able to guarantee the AI will only do the right things, however you define that, and not do the wrong things. So that's sort of a almost philosophical consequence of computational irreducibility. But there's some much more near-term kind of scientific implications. It's sort of a case where, in some sense, science, we have gotten used to the idea that science is about making predictions about things. And computational irreducibility shows us from within science that there are sort of limitations on the level of prediction that we can make. Computational irreducibility is kind of related, I can talk about this a bit more later, to Gödel's theorem and things like that. It's sort of a tightening of those kinds of ideas. So it's something where, in a sense, from within science, we're seeing that there's a limitation of science. There's a limitation on predictions in science and so on. But it's still the case that sort of one of the most surprising things, perhaps, in physics is that physics is possible. That is, that the universe is orderly enough that we can actually have laws of physics that we can stuff into our finite minds and that can make meaningful predictions about how the world works. And what we'll find out is that, in fact, it's a general result of computational irreducibility, that within any computationally irreducible system, there are an infinite number of pockets of computational reducibility. So, for example, in Rule 30, what we're seeing is that there's a certain amount of reducibility on the left-hand side here. There are these periodic patterns. We can make statements about those periodic patterns, even if we can't make general statements about the whole system. And it turns out that the laws of physics kind of slide in as kind of pockets of computational reducibility in this kind of ocean of computational irreducibility. There's much, we'll talk about this, there's much that we won't be able to say about the universe, but the things that turn out to be our laws of physics are examples of things we can say about the universe. And in a sense, that's kind of where our laws of physics fit in, so to speak. Okay, well, let's talk some about physics. One of the questions, sort of a really long-running question in physics, is sort of what's the world made of? It's a question that got debated in antiquity, and sort of there were two schools of thought. Kind of the atomism school of thought, it's all made of discrete stuff, and the kind of the continuum school of thought, it's everything flows like water and so on. And that question wasn't resolved for a really long time. It wasn't until the end of the 19th century that it became clear that yes, atoms and molecules actually exist. Matter is discrete. And soon thereafter, it became clear one could think of light as being discrete. At the beginning of the 20th century, most physicists, and I've only learned this recently because very little of what they did on this was published in the end. Most physicists, all the sort of greats once heard of, thought that space was discrete as well. They just thought it would turn out that everything is discrete. In the first few decades of the 20th century, they tried to make that work. They couldn't make it work. They couldn't make discrete space consistent with relativity. And by the 1930s, people gave up on that. And so the notion emerged that space is something that is just this background, and it's really kind of it's ultimately sort of a manifold all the way down. All one can say, space is just this thing where you can put things down at particular positions, and you can and that space is just this background. Well, so the starting point for what I've thought about so having looked at things like cellular automata and having found that they ended up being very useful models for lots of kinds of things in the natural world, in physics and fluid dynamics, in crystal growth, in biology, and things about growth of organisms and so on, in social sciences, et cetera, et cetera, et cetera. These things ended up being very useful models, and systems like them end up being very useful models in lots of cases in the natural and artificial world. In fact, I would say that one of the things that's been sort of an exciting thing to watch is that over the last, 20 to 30 years, there's been sort of this quiet transition that's happened from a time where the typical models people build of things, if you're making a model of a new kind of thing, the typical model you build is using differential equations and so on, to a world in which the typical model that's built uses programs. And it's kind of exciting for me to see, because it's something I've been sort of deeply involved in and trying to create over the last many years, that this kind of after 300 years of kind of it's just equations, there's kind of like, well, actually we can make a program for that, being the sort of the thing that can represent the foundational model of something. But I had never thought that these kinds of models would be good models of fundamental physics. And maybe I knew too much about quantum field theory and general relativity and things like this, because it never really seemed that these models would fit. And, we look at, and that's what people had actually tried to do, as I've now learnt in the early part of the 20th century. They tried to have, discrete kind of lattice models of space and so on, and they couldn't really make that work. And so what I realized in the beginning of the 1990s, actually, is that you have to go to something lower level than this. In a sense, in a cellular automaton, you already have sort of a built-in notion of space and time. You really have to go below that. You have to go to something where where space and time are emergent features of the system that you have, not things that you've built in. They have to become dynamical in some way. So merging that with the idea that one thinks of things as discrete and computational, what does one end up with? Well, so what I started thinking about, and this is actually the beginning of the 1990s, was what if what's underneath space is some kind of network, where all that's really there are kind of atoms of space. There are just these discrete points, and all we know about those discrete points is how they're related to each other. That is, how kind of which atoms of space are friends with which other atoms of space. We're kind of let's see, just pull up something here. We're just kind of defining something where we say, okay, we're going to define some network where we say there are these atoms of space and they have relations to each other. So the question is, can one start building up space and time and the things we know in physics from something lower level, something below space, where we're just thinking about this discrete network where space as we know it has to emerge from this network? And so I had done a bunch of things on this in the 1990s, and the main thing that I discovered at that time was the emergence of general relativity and Einstein's equations from this kind of approach. I'll tell you about that. But then I wrote this big book called The New Kind of Science that came out in 2002. That is kind of an attempt to understand what science is like if you start from rules and programs rather than from equations. And that book was, I would say, very well received in many fields, except for physics. I had one half of one chapter of that book is about kind of applying these ideas to fundamental physics. And my friends in physics were like, we have string theory. We don't need anything new. You know, so I was I said the market for kind of the things I'm doing here doesn't want this product. I'm going to go off and build products people actually want, like Wolfram Alpha and so on. And so I did that for many years. But then in 2018, I continued to kind of think about these kinds of approaches. And there were aspects of kind of the things that I built in the 1990s to do with networks and networks that underneath space and so on that I wasn't very happy with. In 2018, I made sort of a little bit of a technical breakthrough of realizing that hypergraphs were a better idea to look at than graphs. In the end, actually, you don't need hypergraphs, but it's a good way to get into thinking about it. Hypergraphs remind you something where relations in a graph, there are nodes in a graph and there are edges that relate two nodes at a time in the graph. In a hypergraph, you can have hyperedges that relate any kind of nodes, any number of nodes at the same time. Okay, so let's imagine that sort of underneath space is some kind of network, and that the network evolves by having some rules. Like, for example, this might be a rule that says if you see a piece of network that looks like this, replace it by one that looks like that. Okay, so what actually happens when you do this? Well, this is a typical series of networks that you get by applying that very simple rule. It's kind of conceptually a little bit like a cellular automaton, but it's in no way in detail like a cellular automaton. There's no grid, this is just a network that we imagine represents kind of the underlying stuff in the universe. And kind of the concept here is that this is a model of sort of everything in the universe. It's not that this kind of network exists on top of other things. It's not like there's a computer running this. This is a model, this is a representation of sort of everything that there is in the universe. And that everything we are familiar with, space, particles, all of those kinds of things have to emerge as properties of this network. So this is a very simple case where we're just sort of evolving the network, starting with this initial condition. We're just evolving it. We're building up these bigger and bigger networks. Well, you can ask what's a question like what happens in the end with these networks? You know, you can get all kinds of different strange looking networks. Sometimes you get kind of a clue. Like here's an example of a rule. Let's run that rule for a while. Well, if we run this rule for a while, it turns out it knits this kind of two-dimensional object. It kind of knits this thing that looks like it's kind of limiting to something that's like sort of ordinary two-dimensional space. Or we could try another rule. I don't know what this one. Let's try this one here. This rule, you run it for a while. It'll eventually go towards this thing that's kind of like a two-dimensional surface that's a curved two-dimensional surface. So It's sort of a question: what happens in general with these by applying these rules? And notice, by the way, that in this model, that space is represented by the extent of this hypergraph. Time is the progressive rewriting of this hypergraph. And I think one of the sort of big mistakes of 20th century physics was the idea. It was introduced by Minkowski, actually, because he thought it was a neat piece of math to be able to package space and time together in a quadratic form. I think that was actually a big mistake. And the fact is that time is really a very different kind of thing than space. The fact that we get relativity and so on is a separate story. It's an emergent feature of the system, but at some fundamental level, kind of the progression of time, which in these models is sort of the progressive doing of computation, is very different from the extent of space, which is kind of just the layout of this hypergraph. So, okay, so a big kind of result here is what happens if you just are running these rules and you keep running them, and what emerges when you run these rules generically for enough time and so on. There's an analogy here, which is to think about what happens in molecular dynamics. What happens when you have a bunch of molecules bouncing around? What we know is that it doesn't really matter in great detail the particular interaction laws of those molecules. On a large scale, what emerges are the equations of fluid dynamics, the Navier-Stokes equations. Those generically emerge as the large-scale limit of molecular dynamics. So the question is, in graph rewriting, network rewriting, what emerges as the large-scale limit? Well, there are lots of footnotes and lots of kind of special things, conditions, and so on to say, but fundamentally the answer is that the analogy to what emerges, that from molecular dynamics emerges the Navier-Stokes equations, from hypergraph rewriting emerges the Einstein equations that describe the structure of space-time. So that's kind of the sort of first big thing that comes out here. But let me explain that a little bit more. The first thing to talk about is, well, what kind of a space do you even get from this sort of limit of these underlying hypergraphs? And I will say that the mathematics of this is not fully worked out. Normally when you think about space and you build up geometry and differential geometry and so on, you're working with manifolds. If you look on a fine enough scale in a manifold, it's Euclidean space down there. In our case, we don't have Euclidean space down there. We have a hypergraph down there. And so we have to rebuild geometry. We have to build kind of an infrageometry, an infracalculus that, well, among other things, we'll have to answer questions like, what does it mean to have a curvature tensor in 3.1 dimensions? Things like that. It requires kind of rebuilding this whole tower of mathematics, and we're still at a fairly early stage of doing that. We know a certain amount, but there's a lot more to be built. But let me start off with kind of some of the issues. So all we know is the connectivity of this network. So there's a particular network, and we can lay it out in all kinds of different ways. But the question is, what can we say about, what kind of a space is this network? Well, first thing we might ask is, what's the effective dimension of this space? Well, here's a way to sort of test for that. Let's say we have this network. We start at a particular node in the network, and we progressively expand. First, we go distance 1 away from that node, then 2, then 3, and so on. And at every step, as we've gone r steps away from a given node, we ask, how many nodes are there what is the volume of this ball that we've built? How many nodes are there within distance r from a given node? And then, well, we can see, if we have a two-dimensional grid, for example, we can see that the number of nodes grows like r squared. In general, we can say that if we have such a network, that we can estimate the effective limiting dimension of that network as the growth rate. If we say the growth rate of the volume of this ball is r to the d, in terms of the number of nodes within that ball grows like r to the d, then we say d is what we estimate the dimension of the system to be. Well, we can just look at this. We can actually work this out for some slightly complicated graph, and we can plot, as a function of the r, we can plot what the effective dimension is. In this particular one, I think has effective dimension about 2.6. If we go in, or here's this one here, this is firmly dimension 2, and indeed we find that it is dimension 2 by that way of calculating it. If we have a nested pattern like this, we'll find its dimension is about 1.57 here, etc. But if we look at something like this, we'll find that it isn't the r to the d. It's not a constant r to the d. It has a correction. That correction is proportional to the curvature, the effective curvature of the space. And in general, there's sort of a formula that says that the volume of one of these geodesic balls is roughly like r to the d times 1 minus, and then some constant multiplied by capital R, the Ricci scalar curvature. And already by seeing that, we're beginning to see sort of how we might creep into having Einstein's equations show up, because the Ricci scalar is something that shows up in the Einstein equations. More to the point is the Ricci tensor, which is what we get by looking not just at the growth rate of a ball, but looking at kind of a cylinder where you've defined a line, a geodesic, a shortest path between 2 points, and you're kind of puffing out that path, and the volume of that thing is essentially the Ricci tensor in the direction corresponding to that geodesic. So, but in any case, that's kind of the beginning of sort of an indication of how the limit of these kinds of things might be related to something like general relativity. Well, another big piece of the story of general relativity is energy momentum. The Einstein equations kind of relate the curvature of space to the density of energy momentum. And so the next question is, what is energy momentum in these kinds of models? Well, what is a particle, for example, in these kinds of models? What we imagine, but we can't yet really nail this down, is that a particle is kind of like a topological obstruction in this kind of network. It's kind of like something, let's say you have a fluid, it's like something like the vortex that you can get in a fluid, where that vortex is kind of robust. Even though it's made of different molecules at different moments, it has some kind of topological robustness that allows it to kind of move without change, more or less, through the fluid. And that's kind of what we imagine a particle is like an electron is like in this kind of model. I mean, in a sense, an electron is a packet of pure motion. It's not obvious in a model like this that pure motion is possible. It's not obvious that you can take an object, move it somewhere else, and have it be the same object. But particles, in a sense, are the minimal carriers of pure motion. They're things where an electron, we believe we move an electron from here to there, and it's still the same electron. We don't know exactly what electrons are made of in these models. And in fact, what's becoming clear, I can talk about some recent things I've been doing actually even in the last few weeks about quantum field theory in these models, is that you actually don't even need to know in detail what an electron is like inside. And sort of one of the shocker things is that, well, actually, we don't know in quantum field theory either. When we draw Feynman diagrams and things like this in quantum field theory, those are really kind of representations of kind of causal relations between events that take place. We're not saying this is our model. Well, an electron we kind of imagine as a point particle in quantum field theory, but something like a proton, we don't really have to have an accurate model for what a proton is like. We have to avoid that because we really don't know how to do that, even in quantum field theory and existing particle physics. Well, the surprise to me was that we actually we need to know surprisingly little about particles and so on to start talking about things like energy. It turns out that energy in our models is essentially the density of activity in the network. I should explain another thing. Maybe I won't get into this in too much detail, but one of the critical things is the idea of causal graphs. We have, let's see, we have kind of a notion of kind of events that take place in our system. So an event is a piece of network gets rewritten as another piece of network. This is a simpler example of that. This is an example of just rewriting strings. We've got strings of A's and B's, and we've got events that rewrite BA to AB. Okay? So BA gets rewritten to AB, and what's going to happen here eventually is we're going to sort this string into order. Eventually we'll get a bunch of A's on the left, a bunch of B's on the right. But those yellow things are events that take place. Well, we can make a causal graph that says what is the interdependence of those events. Each event has some A's and B's that come in, and it has some A's and B's that go out. The A's and B's that go out may be later consumed in another event. They're going to be, it's like we can think of the events as functions, and the functions are producing results, and those results might be used when another function might be applied to those results. So there's a causal dependency graph that we can get for how these events causally depend on each other. And so one of the things, and this is sort of how the story of relativity emerges, one of the things that's true about this system, for example, is that it doesn't really matter in what microscopic order those events are applied. You'll still always sort the string from A's first and B's second. But the important point here, and you can think of these different ways of doing the sorting as defining effectively different, let's see if I have a picture of that, defining in effect different reference frames for looking for your definition of what counts as simultaneity in doing these updates. And this is how special relativity ends up emerging in these models. That what really matters is the causal graph of a relation between events. And when you parse that causal graph, you say, well, I'm going to take these events to be simultaneous, and they represent a space-like hypersurface in the language of relativity that correspond to the things that are happening simultaneously. The causal graph defines time-like relations between events. It says this event must happen before this event. For this event to have happened, this event has to have already happened earlier in time. But then kind of the transverse to that is to think about space. Which events can happen simultaneously? That's sort of our definition of space, is which things can be happening simultaneously in time. What things can exist simultaneously in time? In any case, so what we can think of, we can draw these causal graphs. They get a bit more complicated for some of these kinds of, this is a causal graph for a network rewriting system, and there are a bunch of events, the yellow dots there, and there are edges that join those events. And when we're thinking, and so we're talking about energy, it turns out that energy is the flux of causal edges through space-like hypersurfaces. So effectively, we define what we mean by a sequence of simultaneity surfaces, and we say essentially that that energy is the density of energy is proportional to the flux, the number of these edges that cross those space-like hypersurfaces. Momentum is the number of those edges that cross time-like hypersurfaces, kind of vertically drawn surfaces here, or surfaces that are not necessarily actually vertical, but closer to vertical. And it turns out mass, for example, is related to the extent to which these causal edges kind of remain in the same place as opposed to propagating to other places on a space-like hypersurface. So in any case, the basic bottom line, that the qualitative picture is energy is the density of activity in the network. So then, well, let's talk about other kinds of things. Let's talk about how special relativity works. Let's talk about, for example, time dilation, a very, a central phenomenon in special relativity. So what does that mean? Well, we've got let's say in our models, we've got a thing. Maybe it's a particle, maybe it's something else. And that thing is going to just propagate through time. Well, in our models, the thing can't just be sitting there unchanged. The thing has to sort of turn over and be made of new atoms of space at every moment in time. So it's taking computational effort to just sort of exist as the same thing going through time. But now let's say that the thing is moving as well. Well, as it moves, in order to move, it has to recreate itself at a different place in space. And so if we kind of think about this sort of qualitative picture, if we sort of think about this thing, it's got a certain computation budget. It can either use that computation budget just being in one place and being itself and continuing to persist itself, or it can use that computation budget rewriting itself at different places in space. And that's what gives you time dilation. It's that what happens is that when you have when you're using your computation budget to move in space, you've used up some of the computation budget that you would use to evolve in time, and so time effectively evolves more slowly for you. That's a qualitative picture. You can make the math and Lorentz transformations and so on out of it, but that's the qualitative story about what's going on. So another qualitative picture is how gravity works. So in these models, there's a notion of geodesics, shortest paths. You can just take this hypergraph and you can say, I've got 2 points in the hypergraph. What's the shortest graph path between those 2 points? That defines essentially a straight line, the kind of that's sort of one's notion of a straight line. Well, now, let's say you ask, well, what difference does it make to that geodesic, to that shortest path, if there's a bunch of activity in the network? Well, it turns out that activity in the network necessarily deflects that, it changes that geodesic. And what one finds is that in the end, that the change in that geodesic, the amount that you're perturbing that geodesic is you can think of that as being the perturbation to the geodesic associated with a certain curvature in space. The geodesic would be sort of the shortest path in this curved space, and it all works out nicely that it is the Einstein equations relating, in a sense, the density of activity in the network to the deflection that makes on a geodesic path in the network. So that's kind of that qualitative picture. Okay, so, and you can look at all kinds of fun things. You can look at black holes and so on, and you can think about kind of how event horizons occur in these causal graphs and so on. They're basically separations in the causal graph correspond to event horizons. And you can think about the early universe and what that might have been like. And you can kind of imagine that the early universe was essentially infinite dimensional, but gradually sort of cools down to be roughly three-dimensional. And that solves some sort of problems in cosmology and so on. I will say, we don't know why the universe appears to us to be three-dimensional. We can't derive the number 3. I can talk about some directions towards doing that in a few minutes. But one of the things that sort of one's interested in predictions from these models, one of the nicest things that one can do is to just use this model as kind of a way of discretizing the Einstein equations, and just sort of use this as a scheme for doing numerical relativity. Let's see if I can show you an example of that. Okay, this is just a little movie of kind of the very beginning of the universe as it might be in a sort of hypergraph rewriting system. And remember, the actual position of the nodes here in the picture we're drawing is just for the purpose of us being able to visualize it. All that really matters in this system is the connectivity of these nodes. Okay, so we can imagine much later in this universe, and we have to kind of set up the initial conditions very carefully here to make this work. We can imagine a graph that we get much later in the history of the universe, where there are two little tiny black holes here, and we can then see what will happen if we keep on rewriting this network with these two little black holes. And we see kind of the structure of space kind of bubbling around, but we see essentially the force of gravity pulling these black holes together, and eventually they'll merge. And you can make measurements of the kind of gravitational waves that come out from this, and they seem to agree decently well with what you get from general relativity. And in a sense, what's happening here is, normally when you study black hole mergers, for example, you start from the continuum Einstein equations. You typically use Mathematica, Wolfram language, to go analyze that and eventually make some discrete version of the Einstein equations that you then solve in a discrete way. But you're imagining that you have kind of the continuum equations, that you're just representing the continuum equations. Here we're coming up from the bottom. We're starting from this discrete structure, and then we're hoping that we build up enough of that discrete structure that we can see kind of continuum behavior. So and for people who use these methods to do numerical relativity, for them, if there's a deviation from the Einstein equations, it's bad news. For us, it's thrilling, because it would be a case where we can actually try and see the discreteness of space. We can see an effect that's associated with the discreteness of space. Right now, one of the effects that, so many effects depend on the elementary length, the actual length scale, sort of the effective measurement in meters that we could assign to the distance between two atoms of space. We don't know what that is. That's the one parameter in our models. Maybe it's on the order of 10 to the minus 100 meters, something much smaller than the Planck length. That's very small. And it's hard to, it'll take some very clever experiment. People were lucky at the end of the 19th century that molecules were as big as they are, that the methods that existed at that time could actually detect them. Although it's a kind of cautionary tale that Brownian motion had been known for 70 years before it was interpreted as the kicking around of things with discrete molecules. And it's my guess that there are effects that already exist in the literature of physics that would actually reveal the discreteness of space. My current favorite is dark matter, but we can talk about that separately if people are interested. So, in any case, but one of the things that is not dependent on the elementary length is the fact that that dimension is a dynamical parameter in these models. And so you can have dimension fluctuations in the universe. And so there's an interesting question of what would a dimension fluctuation look like in the universe? What kind of strange gravitational lensing would you see if there's 3.01 dimensional space somewhere? Interesting question. I don't know the full answer to that, something we're working on right now. Okay, so let me kind of talk a little bit more about other parts of physics. And I don't know, the other big theory of physics in theory is quantum mechanics. And the question is, in these models, how does quantum mechanics work? And let me kind of give an indication of that. Let's see. So if we, for example, this is sort of a pictorial summary of our physics project. Let's make that bigger. Here's this sort of network rewriting associated with the structure of space here. But one feature of this rewriting is we're just saying there's a rule for rewriting things. And we're saying, apply that rule wherever you feel like. Well, there isn't a unique set of ways to apply that rule. There are many different ways that rule could be applied. Each way of applying the rule, in effect, defines a certain path of history. And so what you can see, if you kind of zoom out, you can see there are many paths of history you could follow. And those paths of history branch, like two different things could happen, or they merge. Two paths of history that have been doing different things end up producing the same state. And that branching and merging of paths of history is what we think gives one quantum mechanics. And it's not something that is a sort of add-in to this model. It's something you couldn't get away without that. Given this model, you have to have quantum mechanics, basically. And what happens is it kind of that's the core distinction between classical physics and quantum physics. In classical physics, you throw a ball, it follows a definite trajectory. In quantum physics, sort of the key idea is there are many paths that are followed, and you only get to make sort of probabilistic statements. So what ends up happening is we make this thing we call a multi-way graph. There are many different applications of multi-way graphs. I've studied a bunch of them, whether it's studying kind of games or something where you're playing tic-tac-toe and there are many different moves you can make, and they will sometimes branch, sometimes merge. There are many, many applications of multi-way graphs. But kind of in this case, what we're imagining is that there are different paths of history for the universe. So one of the concepts that's important is what we call branchial space. So you've got this branching and merging paths of history, but now you can kind of lay out all those branching and merging paths of history. Actually, let me show you an example of, see if we can see this just for fun. There we go. Okay. This is just an example of kind of what roughly you can think about. Should be an example. Let's see. Oh, here we go. So this is kind of showing the thing branching into many paths of history. And what we see here is that we see all this branching and we see some merging as well. But what we're seeing here is this kind of array of different possibilities. And we can think about there being a kind of space, we call it branchial space, that is the way that all these possibilities are laid out. And the way that we think about distances in branchial space is, let's say two things have a common ancestor one step back. We can say they're distance one apart in branchial space. And we build up this kind of whole notion of this form of space that isn't physical space, it's a different kind of thing. It's kind of the space of quantum branches. And it's telling us it's sort of a map of quantum entanglements. The fact that two things came from the same ancestor is sort of the fact that those are entangled. This is a map of the entanglements. This branchial space is kind of a map of the entanglement of quantum branches of history. Okay, so we have this notion of branchial space, and this this is kind of representing all these different possible paths of history. And then we can ask questions like, well, what are the dynamics in branchial space? What is the analog of the Einstein equations in branchial space? What happens if you have activity in the network, energy momentum? What does that do? Well, it turns out that that deflects paths in branchial space. Another thing I should say is, what does branchial space represent? This is not a fully nailed down mathematical result, but the qualitative picture is that that distance in branchial space seems to be basically difference of quantum phase. So essentially, as you move around in branchial space, you're changing the quantum phase. And so what we're then saying is that the presence of energy momentum causes a deflection which causes one to be in a different place with respect to in branchial space, or in effect have a different quantum phase. And so what I'm saying is a lump of energy momentum, so the relativistically invariant version of that will be some Lagrangian density or some action. The presence of action produces a change of quantum phase, which just so happens to be essentially the statement of the Feynman path integral. So the remarkable claim is that the phenomenon that leads to general relativity in physical space leads to the path integral in branchial space. In other words, that what's going on in general relativity and in quantum mechanics is the same phenomenon, just played out in different kinds of space. And in fact, you can combine those kinds of space into a thing we call a multi-way causal graph, where physical space and branchial space are projections of the multi-way causal graph. And that gets you into, well, a bunch of people have been trying to figure out whether that kind of establishes these holographic principles that have emerged in mathematical physics and so on. It looks very promising, but there's many I's to dot, T's to cross to nail that all down. But in any case, then you can ask questions in, let's talk about how we perceive quantum mechanics and all the probabilities that we see in quantum mechanics and so on. When we look at physical space, the claim of these models is that at the lowest level, it's made of a bunch of atoms of space. But we perceive physical space in a coarse-grained way. We aggregate together many, many atoms of space, and so space seems to us roughly continuous. So the question is, what do we do in branchial space? We're big compared to the atoms of space. So we think space is roughly continuous. In branchial space, how can we talk about that? Well, what we have to realize is that we exist in this whole multi-way causal graph as everything else does. And so our minds are also things that we can think of as being laid out in branchial space. And so the basic idea is that our minds span many different branches in branchial space. And it is our big effort to believe that if we want to believe that definite things happen in the world, we believe that because we're aggregating many branches of possibility. Just like we believe that fluids have a definite density and velocity because we're aggregating across many, many molecules. Well, so, I mean, this is a somewhat longer story and certainly not all worked out, but essentially the idea is, so one question is, where does the randomness in quantum mechanics come from? And the basic picture of that is, it comes from the fact that we are where we are in branchial space and not somewhere else. So let's talk about physical space. Physical space, there are many aspects of the universe which are determined by global physical laws. But there are other aspects of the universe that are particular to where we are in physical space. We look at the night sky, the dynamics of gravity will be the same anywhere in the universe, but the particulars of the night sky are the way they are because we are at this particular place in physical space. Well, it's slightly more subtle in the case of branchial space. Oh, by the way, but the other important thing about the night sky is we kind of all agree what the night sky looks like because we're all hanging out on this one particular planet. So in branchial space, there's kind of an analogous thing that we all kind of agree on an objective reality because we're actually all very nearby in branchial space. But there are many possible objective realities that we would see if we were at different places in branchial space. So that's a part of that story. Now, also, you can start in our models, you can start thinking about quantum computing and so on, and you can realize that sort of the big advantage of a quantum computer is that it gets to follow many threads in this many threads of history, many paths in this multi-way graph. That's the good news. The bad news is, at the end, we humans believe that we have a definite thread of experience. We want an answer from the quantum computer. We have to somehow knit those threads of history together. And in our models, we can begin, we're not finished with this, we can begin to see that how that process of what one would usually call measurement in quantum mechanics, how that actually works, and what the relative computational effort of knitting those threads of history together so that we get a definite answer is, as compared to the sort of advantage that we get from having those multiple threads of history. Well, so let me, so that's sort of a bit of a picture of our view of physics right now, and there are many details I can talk about. And by the way, there's an analog of the speed of light in branchial space, which is the maximum entanglement speed. If you have an effect somewhere in branchial space, there's a maximum speed at which it can spread in branchial space. The maximum entanglement speed is related through Planck units and so on to the elementary length. I have a suspicion that the maximum entanglement speed determines the noise floor for quantum computers, or what is observed as the noise floor in quantum computers. And it's one of the sort of mysteries of quantum computing that everybody sees certain kinds of noise and decoherence and so on. People have generally believed that if we could just sort of do the engineering better, we would make quantum computers work. I'm not sure that's correct. I think it's kind of like saying, I've got a telescope, it can see a grain of sand on the moon, if only I polish my telescope mirror well enough. But actually, it can't see a grain of sand on the moon because there's a fundamental physical effect, which is diffraction, that limits the resolution of the telescope. I kind of suspect that there's a similar thing going on in quantum computing. And if we're really lucky, the engineering has been done well enough that we might actually be able to measure the maximum entanglement speed from existing kinds of experiments. I think that is probably overly hopeful, but it's a possibility. Okay, so let me mention a couple of things here, and I'll try and rush through a few other areas of science and the implications of some of the kind of formalism from our physics project on those. But let me rush through another thing. So one of the things that's really kind of weird to think about is, let's imagine that we have successfully found a rule that we can say, okay, we run this rule long enough, we'll get the universe as we know it. That's really weird. You know, you're holding up this rule and you're saying, this is the universe. Then the next question is, well, why did we get this rule and not another rule? And that got me very confused for a while. And then I realized that the way to think about this is that in fact, in some sense, the universe is running all possible rules. Just as I mentioned that the thing that gives us quantum mechanics is the fact that all possible updates can be done, so you can imagine the universe running all possible rules. And in a sense, let's say it's a, here we go. Here's another video about this. Let's say you take all possible Turing machines and you're just running all possible Turing machines from all possible initial states, and you're building up this big network of what happens with all possible Turing machines run from all possible initial states for as long as possible, for as long as you want. This is essentially the object that you get is a thing we call the ruliad. The ruliad is kind of the entangled limit of all possible computations. And it's an object with a lot of structure. You might have thought it's just a big mess, but actually there's all this structure because of the equivalence between different paths that went in it, that branched, but then there was an equivalence, and so they merged again. And this builds up kind of this whole structure to the system. Okay, so the ruliad is kind of an interesting thing because it is a unique object. There's only one of it. It is this limit of all possible computations. Once you have the idea of computation, the ruliad is a necessary object. There's no discussion of whether it exists or anything like that. It says once you have, like, it's, you know, you have the definition of 2 and 2, 2 and plus, and so on, and then you can say 2 plus 2 equals 4 just from the definition of 2's and pluses and so on. Similarly, once you have the definition of computation, the ruliad is a necessary abstract construct. It, in a sense, necessarily exists. Well, so what does that mean for us? Well, the ruliad represents everything that is computationally possible. So among other things, we must be embedded within this ruliad. So then the question is, and the question of what the laws of physics as we perceive them should be, is really a question of what do observers like us embedded in the ruliad perceive about what's happening in the ruliad. And here's kind of my my favorite result of the last few years. What seems to be the case is that for observers like us, it is inevitable that we will observe the laws of physics that we observe, at least in general terms. So what does that mean? So what can we say about observers like us? One thing we can say about observers like us is that we're computationally bounded. Our minds are finite. So if there's all sorts of irreducible computation going on in the universe, most of that we're going to be blind to it. We can't trace all of that stuff. We can only kind of capture some small part of that irreducible computation. We're computationally bounded. It's the first statement about us. Another thing that's important about us is that we believe we are persistent in time, which is in a sense a very weird thing to believe, because in these models we're made of different atoms of space at every successive moment of time. Yet it is our internal perception that we are persistent, that we have a single thread of experience through time. So it turns out that the sort of big surprise is that from those two conditions, that we are computationally bounded and that we believe we're persistent in time, those two conditions alone are sufficient to allow us to derive general relativity and quantum mechanics, and actually also the second law of thermodynamics, from this idea of the ruliad. It's something totally bizarre. I did not see this coming at all. I had always imagined that the laws of physics are just ones that we happen to be dealt and that we can never get to ask why, so to speak. That hasn't been so true of the second law of thermodynamics. The second law of thermodynamics is where we say, well, we've got a bunch of discrete molecules bouncing around and so on, and we ask the question, sort of, why is it the case that we believe that these molecules are getting to be in more and more random positions? After all, in this particular example, the molecules have a definite path starting from this very straightforward to describe configuration. Actually, in the case of the second law, we can kind of simplify things a lot, and we can kind of make everything one-dimensional and so on. We can even end up with something which is basically a cellular automaton, where we're starting off from that sort of simple initial condition, and we're seeing the thing sort of grind itself up into something that looks kind of random. This is a reversible system, so we can see if I have an example. So we can run it forwards in time. And it will sort of grind itself up. We can run it backwards in time. It will grind itself up. But the thing is that the second law of thermodynamics is something which for 150 years people have believed. In fact, lots of work was done on it right in your part of the world, that by Kelvin and by Maxwell and so on, it was that the people believed that the second law of thermodynamics might be derivable from the laws of mechanics. Nobody really managed to nail that down. It's been one of these kind of mysteries in the textbooks of thermodynamics and so on. How does that really work? I think the answer is that what's happening is that the dynamics of molecules is computationally irreducible. And the one thing we know about ourselves is that we're computationally bounded. And so just knowing that we're computationally bounded and knowing that the dynamics of the underlying molecules is computationally irreducible, that basically tells us that as we kind of go forward and let the molecules run, we will get to a configuration that to us that we can't decode. It's as if the dynamics of the molecules has encrypted the initial conditions to the point where mere computationally bounded observers can't untangle it. And so we just have to say it looks random to us. The entropy is increasing, so to speak. Well, so the second law is something we could imagine would be derivable. It was certainly not, I did not expect that general relativity and quantum mechanics would be similarly derivable, that it will be possible to say for observers like us, it is inevitable that we will observe the Einstein equations, that we will observe the path integral. So that, to me, is a very remarkable conclusion. Many details to be filled in, but that's the qualitative picture. Now, there are specifics of the universe, like what's the particulars of the night sky, so to speak. Why do we live in a universe that appears to have dimension 3, spatial dimension 3 right now, etc.? We don't know the answer to that. And my guess is that knowing more, thinking more about what we are like as observers will allow us to nail more of that down. And that in principle, if we were alien observers, very different from the way we are, we might not believe that space has 3 dimensions, for example. Just to give us some sense of how that might work. Imagine even space as we currently imagine it depends quite a lot on a lot of our details. So, for example, if I look around, I can see maybe 100 meters away. Okay. but light comes to us from 100 meters away in a microsecond. So but yet my brain takes milliseconds to process that signal. So for me, it's reasonable to imagine that out there in the world, there is a thing like space, that space is the thing where I can just say there's a state of the universe, there's a state of space, and it exists. And I can sort of gulp in that whole state of space. And then by the time I next think about something, I've got another state of space. If we thought a million times faster than we do, as digital electronics does, for example, this notion of space that we have, probably we wouldn't construct it the same way. So that's kind of the way that you start to see that the way that we construct our physics depends on the way that we are, so to speak. Well, let me very quickly try and talk a little bit about some other areas of science to which this kind of thinking applies. Let me talk about mathematics. So why is mathematics anything like this? What is mathematics? Well, we can think about sort of formalizing mathematics as sort of representing things like transformations between mathematical expressions. So there's a rule for transforming between mathematical expressions. We can say we start from one expression, we build some other expressions. If we want to make a proof, for example, what we're effectively doing is we're saying we make a proof that is a path that says this expression here is related by that relation that I gave to another expression here, to this one here, to this one here, to this one here, and so on. And we can write that out as a proof. And so paths in this meta-mathematical space, the nodes in meta-mathematical space are mathematical expressions or theorems, and the paths are proofs of, for example, the equivalence of expressions or the derivation of one theorem from another. And so we can ask the question, what is the analog in mathematics? In mathematics, as humans have practiced it, we've proved about 3 million theorems. There are about 3 million theorems published in the literature of mathematics. The question is, what's the limit of mathematics as time goes to infinity, when we have an infinite number of theorems? We can start enumerating possible theorems. We can just say, let's take an area of mathematics. These are axioms. Those are the axioms of semigroup theory. That's the axiom of semigroup theory that we can derive two other theorems of semigroup theory from that axiom. We can keep going. We eventually build up this kind of graph that represents where the edges in this graph represent laws of inference from theorems. And this is building up sort of all the theorems of semigroup theory, for example. Let's say we do that for logic. Is this Boolean algebra? No, that's group theory, sorry. Where's Boolean algebra? This one is Boolean algebra. So we're building up sort of this graph of the possible theorems of Boolean algebra. Most of these theorems we as humans couldn't care less about. If we look in this graph of all possible theorems, there are a couple that we care about, that we've given names to. So in a sense, what we're building up here is this meta-mathematical space of all possible theorems, just a few of which we actually care about and we've given names to. Well, the interesting thing is that the space of this kind of limit of this meta-mathematical space, if we don't just take one possible axiom system to start with, but all possible axiom systems, the limit of meta-mathematical space is precisely the ruliad. It's the same object, the same entangled limit of all possible computations that we've said is sort of at the basis of physics. So in some sense, what we're saying is that the foundations of physics and mathematics are the same. And we can start saying, when we look at mathematics as we've practiced it, we can ask, where do typical theorems of mathematics actually lie? And we can actually work out things like, that's the theorem network for Euclid. And that's kind of the derivation of the Pythagorean theorem from set theory. And we can kind of start filling in where are sort of famous theories of mathematics within this meta-mathematical space, effectively within the ruliad. And then there are very interesting things that show up, like, for example, we can make a lot of analogies between physics and mathematics because they're both based on the ruliad. So, for example, one of the facts about mathematics that is surprising is that mathematics is possible. What do I mean by that? It could be that to be able to discuss the Pythagorean theorem, you have to drop down to talking about the definition of real numbers and, really grinding around inside set theory and so on, or even something even lower level, that you couldn't operate at a high level and just talk about the geometry of the Pythagorean theorem. there's an analogy to that in physics, which is if you're doing fluid mechanics, you can successfully do fluid mechanics at the level of talking about velocity fields and things like this. You don't continuously have to drop down to the level of molecular dynamics and start talking about what individual molecules are doing. The fact that higher level fluid dynamics is possible is analogous to the fact that higher level mathematics is possible. And so that's one kind of conclusion. You can also talk about things like the possibility of the homogeneity of metamathematical space. The fact that you can move from one place in metamathematical space to another is kind of like translating all your theorems from geometry to algebra. But the fact, if we believe in homogeneity in metamathematical space, it's kind of telling us that there must exist many dualities between different areas of mathematics. Another thing, just to throw it out there for physics purposes, what's the analog of a black hole in metamathematical space? So a black hole in physical space, the simplest kind of black hole, a Schwarzschild non-rotating black hole, is a space-like singularity where one of its features is that time ends for everyone. So there's a path you're following, a geodesic, and every geodesic ends at the space-time singularity in finite time. So in a sense, everything is bounded, so to speak. Well, what's the analog of that in metamathematical space? In metamathematical space, the paths, in physical space, the paths are where you actually move. In metamathematical space, the paths are proofs. And so to say that all proofs are of bounded length is basically to say that you have a decidable theory, like propositional logic or something. So what ends up happening is that what is a black hole in physical space with sort of all paths ending in with time stopping, that becomes a decidable theory in metamathematical space where all proofs are essentially bounded. And then the really lovely thing, not properly nailed down yet, is that the singularity theorems that say once you have enough energy and momentum in physical space, you inevitably form a black hole. The rough analog of that seems to be once you have enough proof density in metamathematical space, you inevitably get a decidable theory, which means in a sense the future of physics and the future of mathematics are tied together. The future of physics is a universe with a bunch of black holes in it. The future of mathematics is a bunch of decidable theories. So there are lots of analogies. There are lots of things to talk about. I could talk about biology. I made a bunch of progress recently in understanding kind of the foundations of biological evolution. Probably should stop and try and take a few questions, but let me just say, let me show a couple of pictures. Okay, I'm just going to flash up a couple of pictures. This is sort of a very minimal model of biological evolution in which you have kind of the genome on the left. You mutate the genome, you end up getting these different sort of ideas for how the process of evolution works. You end up getting multi-way graphs that represent the possible paths of evolution. It then turns out that kind of the fitness functions of natural selection end up being analogous to reference frames in relativity. So that's that story, and ridiculously shortened story. But another story here is about machine learning and about the role of computational irreducibility in machine learning. And sort of the conclusion there has to do with the fact that in machine learning, you are kind of taking lumps of irreducible computation and gluing them together. And that's kind of how you build up functionality in machine learning, which kind of tells you a bunch of things about what you can expect to say in terms of a theory of machine learning and not. And I'm sorry, I went on much longer than I expected to, but as you can tell, there's a fair amount to talk about. And hopefully we have time for at least a few questions or comments. So thank you very much.
Well, thank you very much, Stephen. We really enjoyed that, and I'm sure we had a lot to think about. So we'll go straight into the Q&A. We have a few minutes for that, hopefully. Perhaps we could start here.
Let me look at my calendar to find out what is, oh boy. Yeah, okay. Yes, we have a few minutes. Please go ahead.
All right, let's look in the room here. Yes, we'll kind of, we have someone in the room. I think we have a couple in the room.
Okay.
Take those in the in-person audience.
Great.
All right.
Hello.
Yes, I can hear you, yes.
Excellent. I don't know if you can see me or anything. Thank you, Stephen, very much. I've been a great admirer of your work and of the physics project for a long time. I'm very interested in inference in Forney-style factor graphs, and in kind of having this big compositional model that you then kind of carve at the joints in order to be able to make inference tractable. I was interested, with respect to the principle of computational irreducibility, I have a question, which is that, let's say, in all of your work and all of your kind of musings, do you have any suspicion that we might be able to look at a system and determine if it is computationally irreducible without having to sort of empirically test, say, the rule 30, let's run it ahead. Oh, gee, we really can't predict anything with rule 30. We have to just kind of do the computation. Is there anything that you might suspect allows us to kind of say ahead of time, rule 30 is computationally irreducible?
No, sadly, that's a computationally irreducible question. I mean,
yes, I thought it might be.
It's like saying, you know, is this undecidable? No, it's undecidable whether it will be undecidable. I mean,
yes.
Basically, you can get indications of these things very easily. I mean, there are many equivalent kinds of questions. It's like asking, you know, is there a modelless way of making a model? No, there isn't. Is there a, you know, is it a, you know, how does this, you know, you can get indications. You know, there are cases where we can get good evidence of things like for example, a very typical kind of thing is to ask to you know, how do you show computational irreducibility? Well, you can do things like, let's give an example here. You can do things like show computational universality. So this is a thing from 2007 of a Turing machine. This is I knew that there were no simpler Turing machines that could be computation universal. And the principle of computational equivalence would suggest the very simplest one that isn't obviously simple in its behavior will be computation universal, and that turns out to be the case. These are sorts of things, but the proof of that is something very complicated. It's kind of so you can get lots of indications. You can do, you know, you can pick away at these things with statistics. You can pick away with other kinds of methods. And you know, even proving that this is computation universal isn't the full story of proving that not every statement about this Turing machine will be computationally irreducible. It's a certain set of statements. One saying that most statements about it will be computationally irreducible. We can talk about what that means. There are computation theoretic results about undecidability that talk about when this is a complicated story. The answer is there's no simple answer to your question. I would love it if there was, but there isn't. That's probably the best I can do in a short time.
Thank you very much, Stephen. It's very good.
Thank you very much. Okay, do we have any other? I think maybe we can take Sphinx's question.
Hi, thank you so much for the talk. I was meaning to ask about waves, because like in classical physics, for example, sound travels through air, which is made out of real atoms, or other forms of matter that are made out of atoms of matter. So the structure and the size of those atoms does impact things like the wavelength and the propagation properties of it. So light and gravitational waves, for example, of course, and also realistically, all particles are waves in the fabric of space-time. So how does that being quantized affect those waves?
Okay, reasonable question. So in that picture I showed you of a black hole merger, you could Okay, so what is a gravitational wave? A gravitational wave is something where there is a variation of curvature, of a certain kind of curvature at a particular position in space. And that variation in curvature sort of varies with position in a wave-like way. You can measure the same kinds of things in our models, and you'll get the same kinds of results. It's like saying if we have a bunch of molecules bouncing around, what is a sound wave? Well, a sound wave, every individual molecule knows very little about the sound wave, but the overall effect of all those molecules bouncing around is to maintain this structure of a fluid in which there can be waves, and a wave can involve a great many different molecules. So it's really the same kind of thing here. Now, for gravitational waves and for For example, the fact that gravitational waves and light travel at the same speed is fairly obvious in our models. We don't really know quite what photons are like, but we can see that the maximum propagation, that the speed at which kind of curvature fluctuations travel is the same as the speed at which other effects can travel in our models. So that's kind of a rough way that works. Now, in the case of sound waves, for example, if you have a sufficiently high frequency sound wave, eventually that sound wave will start probing the distances between molecules, and you won't anymore have the usual rules, the usual so-called dispersion relation for sound. And the same is true here. At a sufficiently, for example, a sufficiently energetic gravitational wave, sufficiently intense gravitational wave, will have differences from what you would expect from continuum space. Unfortunately, those differences only show up when you have kind of wavelengths, I think, only show up when you have wavelengths comparable to the elementary length. So it's not very accessible experimentally. If we're super lucky, there will be some effect which is logarithmically dependent on the elementary length. We don't know that yet. But it is certainly true that in this model, ultimately, the way the gravitational waves are propagating, a bit like the way sound waves propagate in a fluid, they depend on the substrate, so to speak. The idea, in this model, in a sense, space is not a thing brought in from the outside. Space is knitted together within the model itself. And thought about in terms of sort of the traditional views of quantum field theory and so on. In quantum field theory, there's been sort of a mystery of how can there be all this quantum fluctuations in quantum fields that sort of seem to have a lot of energy density associated with them. How can that not cause the universe to curl itself up into a small ball because of all that energy density having gravitational effect? In our models, those effectively quantum fluctuations are what build space-time. And so you don't have that same kind of issue. So that's the rough story. Much more to say about this, but
of course, yes.
Thank you so much.
Great, thank you, Sphinx. We have. Do we have any questions from Harriet Watt, St Andrews, or Aberdeen? If not, we'll take another question from here.
Thank you for the talk. I hope I'm audible.
yes.
Thank you. So my question was related to the ruliad, and please pardon me if I'm ignorant about this. When we talk of states or probabilities, it generally arises because there are a lot of possible states that any given thing could be in.
Mm-hmm.
But what is in this context, especially in the context of the ruliad, then what is a decision that this should be the rule? Is there a way that a decision is arrived at? Because we talk of choice, but then, at least to my limited knowledge, we never talk of a decision.
Okay, so maybe roughly I can say the following. So kind of the idea is we are observers within the ruliad. We are localized within the ruliad. We don't get to observe the whole ruliad. We are simply sampling a tiny part of the ruliad. Our notion of probability comes because we are where we are and not somewhere else. That's why we got the result of the coin toss that we got. There is the other result of the coin toss is somewhere. It's just not where we are experiencing the ruliad. Now, this question of whether of how we make decisions and how we are as observers. I think the key thing about an observer is there's a lot of complicated stuff going on in the world at large, but then the observer is taking all that complicated stuff and compressing it so it fits into their finite mind. So, for example, we might observe all these pixels that we get from all these photons coming in from the outside world, but yet all we perceive is that there's a cat in the picture or something. We are, the essence of observation is the reduction of sort of the details of the world into something that we can have a narrative about. And I think decisions are pretty much the same kind of thing. They are taking kind of all the possibilities of the world and kind of narrowing it down to a particular thing. And I think that's sort of an essential feature of the way this works, is to say that our experience is based on sort of us as observers who sample this tiny part of the set of possibilities. And I think that's roughly how I would approach talking about kind of these questions about decisions and so on. And it is certainly okay. The thing is, we think definite thoughts, and in a sense, we think a series of definite thoughts. We discretize the world into concepts. We use words to describe things. We are making a major compression of the world to turn it into something that we can describe in terms of words. And I think that the way to think about it is that, in a sense, that is the essence of what we're doing as observers. We're taking all this detail, all this complexity out there, and we're just being able to say we have a narrative based on words. And I think that's sort of the story of making, we're choosing this particular thing that we will describe, this particular sampling of the world. That's what we're choosing, and then we choose another one, and so on. And that's kind of, I think that's kind of a way to think about this process. Again, that's a complicated question. That was my best effort in just a couple of minutes to address that.
Thank you very much. I'm sure there are more questions. Maybe we'll take one more question locally, and then we'll wrap it up. I know there are a few others online. Maybe in the chat, Stephen, you'll see these questions. But
yes, I mean, let me just say that for people who are interested in this stuff, there are many resources out there to learn about this. Also, I do live streams where I try and answer questions about different kinds of things. Actually, a couple of times a week I do that. So if you're interested, not too questions that aren't too technical, I sometimes do more technical live streams. I also might say you can find I've had a very exciting time in science recently, and I've been it's really been a lot of fun because the formalism that we built from Physics Project just keeps on having more and more and more applications. And if you're interested in what some of those are, you can find. I can put I write quite a bit about things, and if you're interested, you can find writings.stephenwolfram.com has my various things about biology and machine learning and medicine recently, and the foundations of mathematics recently, and so on. Anyway, okay, another
so
question.
We'll have one brief question, and then we'll conclude there.
Yes.
So my question is, can cellular automata be used to solve the Goldbach conjecture?
Well, not directly. I mean, can these ideas be used? Okay, so there are questions about sort of what can one think about mathematics in these kind of foundational terms. How does one start thinking about mathematics? I'll show you an example of something that I just did very, very recently, actually. So this was just to give you an indication of sort of what happens in this kind of formalized approach to mathematics. This is long ago, I was interested in what the simplest representation of logic is, the simplest axiom for Boolean algebra. And the problem is, that's the result that I got. That's its proof. And if we start saying, well, how do we describe the proof? The proof is really, really complicated. These are sort of rough indications of the steps in the proof. If you start unraveling this proof, it ends up being an 85,000 step proof. And this is kind of showing you that there's kind of, we're at the edge of undecidability. We're at the edge, that's a plot of the number of elements in the different lemmas used in the proof, and it goes for 85,000 steps before finally getting the result. There are many things. Okay, so what's the point here? The point is there are mathematical results where, given the axioms of mathematics, given the way that mathematics has been set up, which I'm not sure is necessarily the only possible way, but given the axioms of arithmetic, for example, there is no guarantee, there's no upper bound on how long how long a proof you might need to construct for the Goldbach conjecture, or even whether there's a finite proof given only those particular axioms. It's my guess that a whole bunch of the theories of the questions that have long been sort of out there in mathematics are actually not decidable from the actual axioms that have been given. In other words, the axioms that have been given, for example, for arithmetic, attempt to say things like x plus y is equal to y plus x. What is that? They're trying to home in on giving axioms which specify the integers and arithmetic on the integers and nothing but the integers. But one of the consequences of Gödel's theorem is that you can't do that. There's no finite set of axioms that allow you to sort of sculpt out just the integers and nothing but the integers. Another facet of that whole thing is that there are statements you can make that will turn out not to be that seem like they're statements of arithmetic, but they turn out not to be reachable. There's no finite length proof that reaches them from the axioms of arithmetic. So my guess is that an awful lot of these questions that have been long hanging out in mathematics are actually, there is no finite length proof. The Goldbach conjecture might be true or not true, perhaps. In there are cases that are a bit easier to see how that might work. Like, for example, if we look at, okay, last thing I'm going to do here, but let's see if I can do this in real time. You know what? I am going to try, since I mentioned this, I'm going to say, draw a picture of the zeta function on the critical line. Let's see what we managed to do here. Let's see if our AI is up to snuff here. No, one feature of, okay, let's try running this. Okay, there we go. Cool. So that was, it just synthesized that Wolfram language code, and then I just ran it. This is the Riemann zeta function, the real part of the Riemann zeta function on the critical line. And the Riemann hypothesis, a long unsolved problem in mathematics, says there's no minimum here that lies above the axis. That's one statement of the Riemann hypothesis. So, you know, the question is, it seems like you can see from this picture why it might be hard to prove that, because it wiggles around an awful lot. And I'm sure if we ran it out a bit longer, it would still be wiggling. I guess the point I'm making is, if you start trying to construct a proof where you go step to step to step, there's no guarantee that that's a finite length. So I think it's what the kinds of things I've been looking at might tell one is something about kind of the empirical metamathematics of mathematics. What one can expect in the structure of proofs in mathematics. And questions like, if you look at proof space, are there holes in proof space? Are there proofs where you can follow one path of a proof but never be able to get to another one? Again, complicated question, and I'm sorry I can't do more justice to it, but that's at least some indication of that.
No problem.
All right, I have got to go back to my day job.
Well, it's been a pleasure having you, Stephen, and I'm sure I represent everyone if I say thank you very much for that very thought-provoking talk. Perhaps we can thank Stephen once more.
Thank you. All right. Nice to see you all. Off to the day job. Bye for now.
Bye, Stephen. All right. So thanks, everyone.